All right, guys, looks like we have a full house today. So this is the Arithmetic Algebra dedicated #1 class. So welcome, everybody. How do you guys feel about math? How do you guys feel? Do you feel confident, not confident? Challenging, scary, not good, pretty confident? Okay, okay. So let me go ahead. We are recording now, so that's good. So you guys, arithmetic and algebra, um, these might seem innocuous or like they're not that big of a deal to some. But on the GRE, they have a way of making even simple concepts kind of complex. So you really have to have a firm grasp of arithmetic and algebra in order to do well on the test. And if you don't, then it becomes very, very difficult to get the score that you want. So I'll even give you an example. Take, for example, like average. All right, that doesn't fall under arithmetic and algebra, but it falls under data analysis. And the GRE has a way to make average like a very difficult problem. So, yes, you understand what an average is. You add up all of the items in a list and then you subtract by the number of items in the list. You understand that. But the GRE has a way to make that concept difficult. The same is true of arithmetic and algebra. So, even if you understand these concepts, they're going to combine them. They're going to try to trick you. They're going to leave traps. So what that means is you can't have like a so-so kind of familiarity with these concepts. You have to have them pretty down. So that's what I'm trying to kind of like emphasize in this class. Now, I don't want anyone to be scared. So you guys are familiar with the ETS Math Review Guide, right? So the ETS Math Review Guide divides arithmetic into integers, fractions, exponents, and roots, decimals, real numbers, ratio, and percent. It divides algebra into algebraic expression, rules of exponents, linear equations, quadratic equations, linear inequalities, functions, applications, coordinate geometry, and graphs of functions. So my original plan was to do the following. So if you actually count these up, we have 7 items here and we have 9 items here. And if you add those together, that's 16. And I was originally planning to have 8 of these lessons, 8. So my original plan was to do 2 of these in every class, like this. However, not all of these concepts are equal. In fact, the integers are something that you have to have down pat. So this entire class is going to be about integers, but more specifically, it's going to be about a kind of integer that I'm in love with a little bit. I think it's the greatest integer category ever created. And hopefully by the end of this lesson, you will also be in love with this category of integer. Okay? So let's just begin this because we don't have too much time. All right. So step number 1, whenever we are talking about numbers, a starting place is going to be the natural numbers. So think about a toddler, someone who's 2 or 3 years old. Whenever they start learning about numbers, do you want to teach them about zero or negative numbers? Of course not. So what we have here are what are known as the natural numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 1,000, infinity, just goes on forever. And in the time of Aristotle, so this is my homeboy Aristotle right here, basically everyone was using natural numbers. Now, is that true exactly? Maybe not. This is a very Eurocentric way of viewing things. There were a lot of Chinese mathematicians that the West was not aware of. There were a lot of mathematicians in India and that region that the West was not aware of. But in the Eurocentric kind of version of history, where Aristotle was the king of math, basically during his time, they were using what were known as the natural numbers. All right. But fast forward about 800 years, and you have what are known as the whole numbers. And notice the whole numbers are very, very similar to the natural numbers with just only one change, but it's an important change. It's the addition of 0 right here. Now, usually the addition of 0 is credited to this gentleman right here who lived in about, what was it, maybe 600 or 700 AD. And I believe he's Indian, and he has a name like Brahmagupta. Brahmagupta. Is that right? Can you Indians back me up here? I'm sure you guys study this guy. No, Rahul, that's not right. I Googled it, unless you guys changed the name. At least in English, the way they spell, yeah, there we go. Aborigine has it. So Brahmagupta. Yeah, so I was pretty close. So what this guy did is something that was actually pretty fundamental. He invented this idea of zero. And you have to understand, at the time, this was like some revolutionary shit. I mean, this was like just blowing people's mind. You may be like, well, how are you going to count nothing? You know, this kind of stuff. Now, again, there is a lot of debate and controversy here. Apparently, there were some Chinese mathematicians using zero maybe hundreds of years before, but Chinese records tended to stay kind of around China. They didn't really spread around the world that much. Anyway, it doesn't really matter. Somebody invented zero. None of us did it. And it's kind of weird if we take pride in something that happened like 1,500 years ago, right? So as you can see, the whole numbers and the natural numbers are very, very similar, except for this addition of zero. We are now going to move into kind of the main component of today's lecture, the integers. So everybody, these are the integers. And you have to understand something about the integers is that now we have zero. We also have these natural numbers, but now we have these negative numbers. And again, I think it's hard to really kind of overestimate how much this shit was just like blowing people's minds. This was just like mind blowing stuff, especially for the Europeans. So even into like the 17th and 18th century, there was a good chunk of European mathematicians who refused to accept negative numbers. They just absolutely refused. Now, this guy right here, he didn't necessarily invent negative numbers because negative numbers have been around for a while. But what this guy did here, I think his name is John Barrel or something like that. What this guy did is he basically invented the number line, or he's usually credited with inventing the number line. So this thing's the number line, and to us, this we take this for granted. We think that this is like something that's so normal. But you have to understand something. You know, putting the negative numbers on the left, putting the positive numbers on the right, putting zero right in the middle. This kind of stuff is easy to see in hindsight once you learn it growing up. But if you actually have to invent something like this, it's pretty revolutionary. So this guy right here is usually credited with inventing the number line. And the point I'm trying to illustrate to you guys is that these steps, step one, step two, and step three. So remember, we started with these natural numbers. We then got to these whole numbers, and then we got to these integers. These were not easy steps to make. These were very fundamental steps in the kind of the way we think about math. So I want you guys to have a greater appreciation of math. I think that's a huge problem. I think we don't study the history of math, and I think we should. The history of math is it makes it so much more interesting, and I think I'm gonna try to prove that to you guys here, the history of math, and I think you guys will start to appreciate it a lot more. So if you guys are actually interested in studying the history of math more, there's a book that I recommend called Journey Through Genius. And this book not only walks you through some of the most kind of fundamental math theories ever created or discovered, but it does so in a very kind of interesting historical context. It shows you how just revolutionary some of these ideas were. All right, guys. So far, what have we started with? We started with the whole numbers, or sorry, the natural numbers. We then moved to the whole numbers, and then we moved to the integers. And so far, all of this probably seems relatively easy, relatively innocuous, but buckle your seatbelt. It's going to get a little bit more challenging. All right, let's move on. So we have something called factors. Now, don't let factors scare you. All right. Factors are basically, if you take like the number 10, factors are the numbers, specifically the natural numbers on the GRE, that basically go into 10. So let me show you what I mean. So you have 1, 2, 5, and 10. So 10 has 4 factors, 1, 2, 5, 10. And let's kind of prove this. Notice that 1 times 10 equals 10. Notice that 2 times 5 equals 10. So these are the 4 factors of 10. Now, some of you guys who are more familiar with math, I know what you're already thinking. You're thinking, what about the negative numbers? So, for example, -1 times a -10 is going to be 10. A -2 times a -5 is going to be 10. And technically, you are correct, but you have to understand that the GRE does not use negative factors. I have never seen or heard it on a test. Does not use negative factors. So whenever we talk about the factors, in like 99% of cases, we're talking about the positive factors. All right. So let's do another example here. So 20. The way that I do factors, let me kind of show you my process, Greg's process. What I do is I start with 1 always. I always start with 1. And of course, 1 times 20 is going to be, 2 of the factors right here. I then go down, or specifically up, and I find the next factor of 20. So in this case, it's going to be 2. Notice like 3 doesn't go in there. The next one is 2. And then it's going to be 2 times 10. Does 3 go in? No, it doesn't. But 4 does go in. So it's going to be 4 times 5. Now, here's the cool thing about this process. Once you find these two factors that are right next to each other, see how close, see how 1 and 20 are very far apart? It's a distance of 19. See how 2 and 10 are very far apart? It's a distance of 8. But now look at 4 and 5. That's only a distance of 1. Once you get them to converge in the middle, that's usually the indication that you are done with this process. So how many factors does 20 have? It looks like 20 has 6 factors. Okay, let's have you guys do an example. How about do 45? So find the factors of 45 using my 2-column process right here. Okay, so take about 1 minute. It shouldn't be too difficult, 1 minute. Okay, so everyone, following the process, remember you have your 2 columns. So there's column 1 and here's column 2. It's going to be 1 times 45. Does 2 go into 45? No, it doesn't. Does 3? Yes, it does. 3 times 15. Notice that the gap here is 44, and now the gap is 12. See, the gap is rapidly shrinking. Does 4 go into 45? No, it doesn't. Does 5? Yes, it does. So 5 times 9. And now the gap is only 4. Does 6 go into 45? No, it doesn't. Does 7 go into 45? No, it doesn't. Does 8 go into 45? No, it doesn't. So we're done. We're done. Okay. We know 9 goes into 45 because it goes with 5. So again, 45 has 6 factors. 6 factors. Okay. Let's do a harder one. All right. Let's clear some room here. I want you guys to find me all of the factors of 240. Okay, so use the 2-column process and find all of these factors. Okay, guys, I'll give you 2 minutes for this one. Okay, everybody. So we're just going to follow this process. So we have 1 times 240. And notice the gap is 239. We then have 2 times 120. And now the gap is 118. We now have 3 times 80. And the gap is going to be 77. We then have 4 times 60. And the gap is going to be 56. Notice that this gap gets smaller and smaller. We then have 5 times 48. And the gap is going to be 43. We then have 6 times 40, and the gap is going to be 34. So we still have somewhat of a gap here. So we're not done, but we're getting pretty close. We're making good progress here. So next we're going to have what? So 8. Okay, so 8 is going to go in 30 times. So that's going to be a gap of 22. We're then going to have 10. The gap is going to be 14. So we're getting closer and closer and closer and closer. We then have 12 and 20. The gap is going to be 8. Oh, we're so close. We're so close. And then finally, what are we missing? How about 15 times 16? And notice the gap is 1. Boom. Pretty cool, right? So every time you do this 2-column process, the gap gets smaller and smaller and smaller and smaller and smaller. And in this case, the gap kind of culminates at 1. So how many total factors do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you times all of that by 2, and you get 20 total factors. Okay? Any questions about this process, guys? Any questions about this? No, it does not always end with a gap of 1. No. But it does end with the gap being as small as possible. So good question, Angel. Okay, we have a question from Vinay. Hey, Vinay. You there? Vinay? All right, going once, going twice. Okay. What is the function of finding the gap? The gap allows you to determine when you're near the end. So notice when the gap is big here, that tells me, oh, I still have a lot more factors to find. But as I get closer to this gap being smaller and smaller and smaller, I know that I'm almost done with finding all of the factors. Okay, Momina, does that make sense? It's like a signal. It's like a signal. That's what it is. Okay. The next concept, everybody, is multiples. Now, multiples in some respects are going to be like the opposite of factors. So take 10, for example. We talked about the factors of 10 being 1, 2, 5, and 10. The multiples are when you basically don't go down, but you go up with the numbers. So everyone, here's kind of a trick question. And before you answer it, I want you to really think about it. What is the first multiple of 10? What is the first multiple of 10? It's kind of a trick question, guys. So if you're saying 10, you're answering too quickly. Okay, the correct answer is 0. At least that's how I think of it. So everyone, remember what a multiple is. A multiple is you take your starting number. Okay, you take your starting number, and what you do is you multiply it by one of the whole numbers. Okay, you multiply it by one of the whole numbers. And remember, the first whole number is 0. So when you have your starting number of 10, 10 times 0 is going to be 0. Okay, 10 again, 10 times 1 is going to be 10. 10 times 2 is going to be 20. And we'll do one more example here. 10 times 3 is going to be 30. So don't forget that 0 is, in fact, a multiple of 10. A lot of people forget that. So be very careful because that could come and bite you in the ass. Don't forget that. Okay? All right, any questions about that? Okay. Are we good? A multiple is basically, I can tell you how I define it. I can tell you how I define it. Remember, I'm not a mathematician. That's not how I operate. You know, I studied political science in university. So some people find that refreshing because I don't kind of come at math from this mathematician angle. Some people find it annoying. You can't make everybody happy. The way that I define a multiple is basically you take the starting number and you multiply it by one of the whole numbers. That's how I define it. Okay. You take your starting number, you multiply it by one of the whole numbers, and you get a multiple. So is 0 a multiple of any number? Well, yes, because if you multiply anything by 0, you're going to get 0. Okay. Now, some of you guys might be asking about negative multiples, like take, for example, -10, -20, things of that nature. So even if these are multiples, I haven't actually looked up the actual definition. Are these actually multiples of 10? Remember, my job is to teach you GRE, and GRE never does this. GRE never does this. So you don't need to worry about it. Again, I'm not a mathematician, right? So I'm not going to get into the nuances of negative numbers here. I'm just going to tell you what the GRE does, and the GRE does not use negative numbers in this context. Okay? So hopefully that makes sense to everybody. Now, we have two concepts that we have to talk about. We have what's known as a greatest common factor and a least common multiple. So if you take, for example, the numbers 10 and the numbers 20, and then you get the factors of each one. So remember, the factors of 10 are going to be 1, 2, 5, and 10. The factors of 20 are going to be 1, 2, 4, 5, 10, and 20. The greatest common factor is you find all of the factors that they have in common. So 1, 2, 5, and 10. 1, 2, 5, and 10. And you take the biggest one. So the greatest common factor in this case is going to be 10, everybody, because obviously there's a 10 here and there's a 10 here, okay? The least common multiple is kind of the same thing, but instead of trying to find the biggest number, you're trying to find the smallest multiple possible. So take, for example, if you have 7 and 5. The multiples of 7 are going to be, I'm going to start with 7 times 1. 7, 14, 21, 28, 35. The multiples of 5 are going to be 5, 10, 15, 20, 25, 30, and then finally it's going to be 35. Notice that they have nothing in common from all the way here to all the way here. But then when we hit the 35, we finally get the least common multiple. Okay. Now, why are we talking about all this stuff? We're talking about all this stuff because GRE freaking loves it. You guys would be surprised at the number of questions that deal with factors, the number of questions that deal with multiples, the number of questions that deal with kind of a very firm understanding of integers. And like I said, you guys, not you guys specifically, I just mean GRE test takers, they tend to take this stuff for granted. They tend to take it for granted. And it's much more involved than people think it is. So I really, really want you guys to spend a lot of time with integers, factors, multiples, things of that nature. So Jane said, why didn't you start with 0? Okay, so 0 right here. So yes, technically the least common multiple would be 0 here. But remember, that actually doesn't give us any information because the multiple of everything is 0. So as a convention, whenever they're talking about least common multiple, they don't include 0. Does that make sense, Jane? Okay, it's just as a convention. All right, Saman has a question. Hey, Saman.
Actually, I want to ask about the 7 and 5th one. Here, 35 is both LCM and HCF, right?
What did you, HCS? What's that?
I mean, highest common factor or greatest common factor.
Oh, no, we never. Okay, no. So in this case, 7 and 5. Okay, good question. Remember, whenever we talk about factors, we're talking about numbers that are usually smaller than, right? So what are the factors of 7?
7.
So 1 and 7, right?
Yeah, exactly.
Right. What are the factors of 5?
1 and 5.
Right. So what would be the greatest common factor? Well, they only have 1 in common.
Oh, okay. I
Yeah.
got it.
So remember, greatest common factor doesn't go above the number, it goes below the number.
All right. Thank
Okay.
you.
Does that make sense?
Yes.
Okay. Good question. Good question. Okay. Yeah. So Rahul says in India, they teach greatest common factor as highest common factor. Yeah. I mean, there's different ways to say these things, guys. You know, it's just basically potato, potato, tomato, tomato. All right. So now we're going to get into something called intervals. So occasionally on the GRE, they're going to give you two integers. So for example, they're going to say, you know, there's a range from 12 to 27. And in order to solve this problem, you have to know how many integers are in the middle. So the number of integers. And they might include a word like inclusive. The word inclusive tells you that you should include the numbers 12 and the numbers 27. Now, this seems like such an easy thing, right? But this is how GRE kind of messes with people. If you're trying to find the number of integers from 12 to 27, most people's instinct is going to be, okay, 27 minus 12. Oh, yeah, 15. The problem with this is it's not correct. And let me kind of illustrate this to you with an easy example. We're all familiar with the numbers 1 to 10, right? 5, 6, 7, 8, 9, and 10. How many numbers do you see from 1 to 10? 10, right? Obviously, that makes sense. But if we use our little subtraction technique, if we just say, oh yeah, 10 minus 1 equals 9, notice that 9 is not the correct answer. There's not 9 numbers here, there's 10 numbers here. So what you have to do with this formula is you have to add 1. So it's going to equal 10. So don't forget to add the 1, everybody. Adding that 1 is very, very important. All right. So here it would be 27 minus 12, which is going to be 15, right? And then don't forget to add the 1 plus 1. That's going to equal 16. Now, if we ever doubt this, we can always confirm it. Okay. So we have 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. Now, if I'm correct, there should be 16 numbers here. If there's not 16 numbers here, then I did something kind of fundamentally wrong, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, everything checks out. Very good. Now, you might be asking, what if GRE doesn't say inclusive? What if they say exclusive? Well, what that means is you don't include the 12 and you don't include the 27. So it would be from 13 to 26. But I have to be honest, guys, I've never seen them use the word exclusive ever. So if they say nothing, if they don't say inclusive or exclusive, you have to assume that it's inclusive. Okay, so this is a relatively straightforward thing, right? I just don't want you guys to be tricked. Here's a harder problem. Here's a harder problem. From 12, okay, to 96. So from 12 to 96. How many multiples of 3 are there? Before I tell you how to solve this, see if you can solve this by yourself. So from 12 to 96, how many multiples of 3 are there? I'll give you guys 2 minutes. Okay, everybody. So this is very similar to what we did to here. So we take the 96 and then we subtract the 12 and then we're going to add 1 over here. The problem is this is a very big number and it just doesn't make sense. So what you have to do is you have to take this last number, subtract out the first number, and then you have to divide by the multiple 3 right there. That's what you have to do. This is the formula. So it's going to be 96, which is the last one, minus 12, which is the first one. Divide that by the multiple and then add 1. And so what's that going to equal? That's going to equal what? 84 divided by 3 plus 1. Now, what is 84 divided by 3? It looks like it's 28, right? Because think about it. 27 times 3 is 81. 30 times 3 is 90. And then we have to take away 2 of those 3s to get to 84. So it's going to be 28. So 28 plus 1 equals 29. So we have 29 multiples of 3. Okay? Now, this begs the question, what if instead of 12 to 96, I said 12 to 95? What do you do then? I just removed one of the multiples. So we know that the answer has to be 28. We know that because I removed one of the multiples. But now the question becomes, what's the formula? What's the formula, everybody? So it's not the same, okay? If you do 95 minus 12 divided by 3, this thing right here is going to be a decimal. And if it's a decimal, we're not dealing with integers, right? So this is not correct, okay? So what you have to do is you actually have to find the last multiple closest to 95. You actually have to find that. That's your job. So instead of saying 95, you have to say instead 93 because 3 goes into 93 and it does not go into 95. So everyone, the formula is going to be 93 minus 12 divided by 3 plus 1. So it's going to be 81 divided by 3 plus 1. It's going to be 27 plus 1 equals 28. Now I'm going to give you a problem right now to solve this by yourself. So before I do that, does anybody have any questions about this process? All right, we have a question from Ahmed. Hello.
Hello.
How are you?
I'm fine. How are you doing?
Good.
Yeah. Okay. The problem you gave, like the first problem, 12 minus 96.
No, it's not minus. It's 12 too.
Yeah, 96 and between 96 and 12, how many multiple of 3s are there, right?
Right.
So okay, I did it like I subtracted 12 from 96 and then added back 1. So I have got 85 and then divided by 3.
Did you get the right answer?
I didn't get the right answer. So what's the problem?
So the problem is you're adding the 1 before you're dividing. That's the problem.
But I don't understand, like why is that a problem? Like,
are you familiar with PEMDAS?
Yeah, I'm familiar with the PEMDAS.
Okay, so you do the parentheses, right, before the addition, right? You do the division before the addition.
Okay, thank you.
Yeah, so what you have to do is you have to divide it before you add. Does that make sense?
Yeah, it makes sense, but I thought like since we are like finding out the numbers between 96 and 12, so adding back 1 and then dividing by 3 would give me the same answer.
You always have to do PEMDAS or PEMDAS, always. Yeah. Okay, cool.
Okay. Thank you.
Makes sense?
Yeah.
Okay.
Yeah.
All right, guys. So I'm going to give you the own problem now, my own problem. Okay. It's Rahul, it doesn't matter. Division and multiplication have the same kind of thing. Yeah. So they say PEMDAS because it's easier to say. rather than pedmis. Okay. All right. So what I want you guys to do, I want you to find the multiples of 4 from 13. That's a 13, not a B, to 125. Okay, everybody, I'll give you 1 minute. Okay, everybody. So we have to find the nearest multiple of 4 to 125 because 125 is not a multiple of 4. So 124 is a multiple of 4. We have to find the nearest multiple to 13 that's bigger than 13. Remember, we went less than 125 but bigger than 13. So that's going to be 16. And then we're going to divide that by 4. And then don't forget to add 1. So this is going to equal 108 divided by 4 plus 1. 108, what is that going to equal? 27? Is that right? 27 plus 1, and that's going to equal 28. I saw a lot of people using 29. I saw that from a lot of people. I think I saw this like 12 times in the chat box. Ha! Welcome to GRE, everybody. Take nothing for granted. Take nothing for granted. It's so easy to make a small mistake, isn't it? Do you guys see how easy it is to make a mistake? I'm not saying you guys are bad at math, right? Even I could have made a mistake. Let me double check my work here. Okay, so 124 is a multiple that's less than 125. 16 is the next multiple because 12 would be 1. Okay, 124 minus 16, 108, 4. Okay, it looks like it makes sense. All right, so 4 times 25 is going to be 100. I need 2 more 4s, so that would be 27. 27 plus 1, 28. Yeah, so it looks like it checks out. So be very, very careful, everybody. Okay, we have a question from Rowan here. Hello? Rowan, are you there?
Yeah, I'm here. Sorry.
Hey, how are you?
I was just wondering when you said we can't do 12 because that would be 1, what did you mean by that?
I said you can't do 12 because it's not included in this range.
Oh, okay.
See how 12 is outside and see how 128 is outside?
Yeah.
So we can't use 12 or 128.
Got it. That
Okay, makes sense?
Thanks.
Okay, good question. All right, guys. So I got to be honest. This is not what I wanted to talk about. All of this is building up to maybe my favorite topic in the world about math. Any predictions? What do you think is my favorite topic in the world about math? Yes, Rahul knows. It's the primes. I love them. The primes are so freaking cool. The primes. The prime numbers. So the prime numbers are going to be these numbers that only have 2 factors. Okay, everybody? The prime numbers only have 2 factors. And the prime numbers are freaking amazing. So the first prime number is going to be 2. Notice that the 2 factors of 2 are 1 and 2. The next prime number is going to be 3. Notice that the 2 factors of 3 are 1 and 3. Is 4 a prime number? Well, let's take a look. It has a 1, it has a 2, and it has a 4. So that is not a prime number, because remember, the definition of a prime number is it only has these 2 factors, right? Well, this doesn't have 2 factors. This has 3 factors. So that's not a prime number. 5, 1 and 5, 7, 1 and 7. So let's expand our definition a little bit. A prime number is not only one that has 2 factors, it's also a number that only has 1 and itself as a factor. Only 1 and itself as a factor. That's it. That's all it is. So let's list the first, I don't know, 15 primes. You should have these memorized, okay? So it's going to be 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, what is it, 37, I think that's the next one. 41, I believe, is the next one. 43, 47, right here. These are all the prime numbers from 0 to 50. You should have these mostly memorized because they're going to make your life a lot easier. Notice that, like, take 41, for example. If you actually look at the factors of 41, you're only going to find 1 in 41. 2 doesn't go in there, 3 doesn't go in there, 4 doesn't go in there, 5 doesn't go in there, only 1 and 41. Now, you guys don't realize how cool the primes are. They're just so freaking cool. And that's what I want to spend the rest of the lecture talking about. So first of all, okay, the primes go on forever. They never stop. And do you know who proved this? My man Euclid, 2,000 years ago. So this is Euclid. Okay. My dude, right? 2,000 years ago, this guy was living, I don't know, somewhere around the Greek Isles. And he proved beyond a shadow of a doubt that the primes go on forever. And I'm going to show you that proof right now. So those of you who are not familiar with mathematical proofs, don't be scared. It's a relatively simple proof, and it's freaking mind-blowing, okay? So I want us to start with the idea that the primes are not infinite. So the primes are not infinite, all right? And let's imagine that the only primes we have are 2, 3, 5, and 7. 2, 3, 5, and 7. Okay, these are the only primes we have. There's only 4 primes. That's all we got. So what Euclid did is he said, okay, if these are only the primes we have, these are all the primes, right? What I can do is I can multiply all of these together, 2 times 3 times 5 times 7, and then I can add 1. Now, the reason he's adding 1 is because what this does is it guarantees a new factor. It guarantees a new factor in the resulting number. And actually understand why. Because 1 is smaller than 2, 1 is smaller than 3, 1 is smaller than 5, and 1 is smaller than 7, notice that no matter what we do, this resulting number has to be or has to contain a factor that's not included in this list. Again, remember, we know 2 goes into this number here because we have the 2. We know 3 goes into this number, we have the 3. We know 5 goes in, we know 7 goes in, but then when we add this 1, well, 2 doesn't go into this new number because all we did was add 1. If 2 is going to go in, we would have to add 2, right? Not 1. But we're adding just 1. Okay, so 2 doesn't go into this new number, 3 doesn't go into this new number, 5 doesn't go into this new number, 7 doesn't go into this new number, so there must be a new factor built into this new number. Well, let's take a look. 2 times 3 is going to be 6. 5 times 7 is going to be 35. 6 times 35 is going to be what? 210, is that right? I believe that's correct. So 30 times 6 is 180. Yeah, it looks like it's going to be 210. Now, notice something about this. If we list the factors of 210, okay, let's go ahead and list them. So we have 1 and 210. We have 2 and 105. Does 3 go in here? Yes, it does. 3 and 70. Right here. Does 4 go in here? No, it doesn't. Does 5 go in here? 5 and 42. Right there. Does 6 go in there? Does it have a 3? Does it have a 2? Yes, 6 does go in. Let me get my calculator. Hold on. 1 second. See, there's no shame in using a calculator. All right, calculator. So 210 divided by 6. Okay, 35. So there's our 35 right there. Okay. So we have 6 and 35. Okay, does 7 go in here? Yes, it does. 7 and 30. Right there. Does 8 go in here? No, it doesn't. Does 9 go in here? No, it doesn't. Does 10 go in here? Yes, it does. So it's going to be 10 times 21. Does 11? No, it doesn't. 12? No. 13? No. 14? Okay. So I think we're getting pretty close here. Just let me Google it. I just don't want to make a mistake. Factors of 210. Okay. All right. 14. There it is. So 14 and 15. Okay. 14 and 15. Okay, so 7, 15 times 2, 7 times 3, 5 times 3, 21 times 2, 35, 105. Okay, hold on 1 second, everybody. I'm getting lost in my math. 1, 2. All right, let me give you an easier example. Okay, this is not your fault. This is my fault. I started out with a little bit too hard of an example. So if we imagine that the primes are not infinite, the primes are not infinite, and then we have the numbers 2, 3, and 5 right there. So we multiply these together, 2 times 3 times 5, and then we add 1. What do we get? We get 31 right there. Oh, I know what I did. I forgot to add 1. That's why. Guys, remember the 210 number? I forgot to add 1. Okay, anyway, the easier example is better. Okay, so remember here, we know that we have a new factor. This guarantees a new factor. It guarantees a new factor right here. Okay, now here's the cool thing. This new factor right here, this new number, 31, notice that this is a new prime number. Remember, our original belief was that the primes are not infinite, right? We're saying, okay, these are the only 3 prime numbers. But by creating this new number, we have thus discovered a new prime number. And this always works. This shit is so crazy. Like here, like create your own example, all right? For example, just choose like 3 prime numbers. So you choose 3, 5, and 7, for example. Okay, watch what happens. So you multiply these 3 together. That's going to be what? 105. Okay, 105. And then what you do is you add 1. Okay, and you're going to get 106. Inside here is a new prime number. Inside here is a new prime number. This always works. Do you know what 106 equals? It equals 2 times 53. 53, everybody, is a prime number. Isn't this amazing? I don't know if you guys find this as interesting as I do. It's like freaking crazy. So Euclid 2,000 years ago, just by, this little kind of brief kind of math exercise, this little mental exercise, he illustrated to the world that the primes go on forever. Okay, let's use one more example here. So let's use 5 and 7, a very easy example. So we do 5 times 7 plus 1. That's going to equal 36. The factors of 36 are going to be what? Let's do our little 2-column trick here. So we have 1 times 36, 2 times 18, 3, look, right there. 3 is a factor. So notice that 3 is not in our list. So we just discovered a new prime number. A new prime number. Okay? So what Euclid did is he used this kind of what's proof by contradiction. Basically, he said, okay, I imagined that the primes were not infinite, but then I found this contradiction. I found a new prime. So the only thing I can conclude is that my original idea was wrong. My original idea was wrong. And remember, the original idea was the primes are not infinite. All right, let's just do one more example here, okay? Imagine that the only primes we have are 2 and 11. These are the only primes that we have. So what we do is we multiply these together to create a new number. We then add 1. Remember, we're adding 1 because it guarantees that 2 is not a factor and 11 is not a factor. So what this does is it guarantees a new factor. A new factor. So what does this number equal? This equals 23. And what do you know? 23 is a prime number right there. So if we found a new prime number, the only thing we can conclude is that our original idea that the primes are not infinite is wrong. Is that cool? I don't know. Is that just me? See, I think we teach math the wrong way. I think if we focus more on these dudes, I think if we focus more on these guys, math just becomes a hell of a lot more interesting. I mean, the way we teach math is so dry and so bland, but can you imagine Euclid like 2,000 years ago figuring this out? And do you know why do you know why the primes are so cool? Like, let me show you some other stuff that's really cool about the primes, okay? So this right here is the largest known prime number right now. This is the largest known. Look how big this number is. This number is so huge, okay? It has 24,862,048 digits when written in base 10. It was found by Patrick LaRoche of the Great Internet Mersenne Prime Search in 2018. This number was only found, 2 years ago? So we are still looking for these guys. Even with like the most powerful computers and all of this crazy stuff, we're still looking for this. So the prime numbers, even today, still challenge us. Now, before we call it a day, let me show you a couple more cool things about primes, okay? Do you guys know what this is right here? Do you know what you're looking at? It's the periodic table. So these are called elements. And basically, the elements can be kind of considered the building blocks of matter. The building blocks of matter, okay? Do you guys know what this is? What are we looking at here? Okay. This is like the Korean alphabet. So the Korean alphabet, these are basically these letters, these are basically the building blocks of words. Okay? The building blocks of words. All right, I'm going to tell you guys something that's like so fucking cool. It is so cool. The primes are the building blocks of numbers. It's like they're the periodic table or the Korean alphabet of numbers. Take any number you want, any number, I don't care what it is, 25, you can build it with primes. 5 times 5. 2 prime numbers right there. Take any number, I don't care what it is, 33. You can build it with primes. 3 times 11. Take any number, I don't care what it is, you can build it with primes. So 10, 10, 2, 5, 2, 5. See that? We're building everything with primes. So here, let me give you guys a little bit of an exercise. How would you build 50 with primes? How would you build, let's use 76 with primes? And how would you build, let's say, 81 with primes? So go ahead, give me the prime number building blocks of the number 50, 76, and 81. Okay, I'll give you guys 2 minutes. All right, so 50, how do you build this with prime numbers? How about 5 times 5 times 2? Boom, right? How about 76? 2 times 2 times 19. Boom, prime numbers. How about 81? 3 times 3 times 3 times 3. 3 to the 4th power. Now, here's the cool thing, guys. If primes are infinite, remember we just proved that with Euclid. Primes are infinite. What that means is the building blocks are infinite. And if the building blocks are infinite, that means numbers are infinite. And I know you guys know that, but have you ever actually like sat down and thought about why? Why are numbers infinite? They're infinite because the building blocks are infinite. If you have infinite building blocks, you by design have infinite numbers. So this is where the math just gets like really crazy. You know, relatively simple concepts, but kind of a mind-blowing thing, right? And then finally, the last thing I want to show you guys, and then we'll call it a night. This stuff, what we're doing here, breaking a number down into primes, allows us to do lots of cool shit. Lots of cool shit. Cool shit number 1, okay? You can use the prime breakdown to find the total number of factors. To find total factors. Okay, let me illustrate this with an example. All right, take 24. So if we do our little 2-column method, we have 1, 24, 2, 12, 3, 8, 4, 6. How many factors? 8 factors. If we break this down into its prime numbers, okay, it's going to be 3 and 2 to the 3. So 2 to the 3 times 3. Okay, watch this. If we take the exponent right here and we add 1, and we take this exponent and we add 1, okay, 1 plus 1, what we're going to get is 4 and 2. If we multiply these two together, we get the total number of factors. Okay, let's illustrate that with another example. All right, let's take 30. So the first thing we do is our little 2-column method. So we have 1, 30, 2, 15, 3, 10, 5, 6. So again, 8 total factors. If we break this down into the primes, what are we going to get? We're going to get 3, 2, and 5. So it's going to be 2 to the 1, 3 to the 1, 5 to the 1. See each of these exponents? Add 1. So 1 plus 1, 1 plus 1, 1 plus 1. And you get 2 times 2 times 2. And what do you know? It equals 8. So I think, hopefully you guys are understanding why I'm so in love with the prime numbers. Okay, let's do a more challenging one. How about this one? 360. Now this number, if you try to do the 2-column method, you're going to find that it's very, very difficult. It gets very long and very tedious. So what I want you to do is I want you to break 360 into its prime numbers and do this trick here. How many total factors are in 360? All right, I'll give you guys 2 minutes here. All right, everybody. So what we do is we split it into the primes. Okay, so I'm going to say, let's say 6 times 60, and this is going to be 2 and 3. What's this going to be? 6 and 10. This is going to be 2 and 3, and this is going to be 2 and 5. So how many 2s do we have? Looks like 3 2s. 2 to the 3, okay? How many 3s do we have? Looks like 2 3s, and then we also have this 5. So we add 1 to every exponent, and we're going to have what? 4 times 2 plus 1, which is 3, times 1 plus 1, which is 2. And what does that equal? Well, that's going to equal 24. 24 total factors. Okay? Now, this class, I wanted to show you a lot of other cool stuff you can do with the primes. So I'm just going to give you a little bit of a tease, like a taste. You can also use the primes to find the greatest common factor between two numbers. You can also use the prime to find the least common multiple between two numbers. Okay. And then finally, I had a bunch of GRE questions here that deal with prime numbers. So how about I give this to you as homework? So all of these questions deal with prime numbers. You know, my favorite. Okay. So everyone, get out your phones. Get out your phones. All right. Get ready to take some pictures. And I'm also going to put this on the Discord channel as well, so don't worry about that. Okay, so go ahead. I'll stay on each slide for about 10 seconds or so. Okay, that gives you time to take a picture. All right, beginning now. All right, next one. Okay, next one. Next one. Okay, next one. And I think this is the last one, everybody. Yeah, so the next class I think is on the 13th, but I'm not really sure. Have this done before the next class, everybody. Okay. Oh, Rowan, the Discord link isn't working. Okay, I'll update it. Thank you for letting me know. All right, guys, I will stay here for about 5 more minutes in case anybody has any questions. Let's see. We have a question from Trishanon. I don't know if I'm saying that right. Hey, Trishanon.
Hello.
Hey, how are you?
Hey man, I'm good. I just had a question. Uh, is this recording classes? Will we get the recorded classes?
Yeah. I record all the classes.
Yeah. It's saying it's recording. So, will we get the clip? Because I missed part of it. Like my power went off. So
Yeah. It'll be up there in probably about, I don't know, 12 hours or so.
yeah, cool.
Yeah.
So it was on the website, right? Like
yeah, it'll be on the website. Yeah.
All right. So I think in the list of classes or somewhere, right?
No, it'll be under recorded classes. But if you guys, I don't know if you guys have noticed in the member area, I now have the new content feed. Have you guys noticed that? So every new class, it gets onto that new content feed. So that kind of, if you want to stay most up to date with GregMat Plus, that's where you go.
Where is it exactly? Like,
it's just right on the member area. Like if you click on member area, you'll see it right in front of your face.
Okay, sure. I'll explore it and go through it.
Okay.
Thanks.
Cool.
Sure. Cool.
All right. Any more questions, guys? Any more questions? Saman. Hey, Saman.
Actually, Greg, it's like a general question, not related to today's topic.
Sure.
Some of my friends, they are preparing from third party, like GRE materials. I honestly am not in favor of third party, and so are you, I know that. but they are saying that these 5 pounds and all these things, except for the ETS ones, I'm specifically talking about the 5 pounds. They are saying the questions, they have become like obsolete, and they no longer help you increase your scores. So is it so?
Are
what
your
is your
friends
opinion?
at a test center called? What's the name of the test
I know
center?
what. No, actually, they are just tutoring from some of our teachers who have already taken GRE. They are not experts, but some of my friends. Yeah.
I made a comment on Reddit the other day, and I forget what I said. I think I said, you can use the 5 pound book for math or whatever. And somebody responded that the 5 pound book is now obsolete. They used that exact word, the same word you just used.
Mm-hmm.
So
This is honestly not my opinion.
No, I'm
but
just
I
wondering
wanted
who
to.
said that. I
Oh,
wonder. Yeah, I wonder if this is some kind of like third party like talking point that's going around.
I honestly don't know, but I had this thing in my mind, and I just wanted to ask you because I know you are GRE expert, so I would go for what you are saying.
I think
just
the 5
wanted.
pound math book is good. Yeah, I like it.
Okay, then I will definitely follow it.
But don't do the verbal. Don't do the verbal.
Oh yeah, I'm not doing verbal from it. Yeah, maths. Thanks a
Yeah.
lot, Greg.
Okay, no problem. All right, any more questions, guys? Connie? Hey, Connie.
Hey, Greg. When is this class going to be up on your website?
Do you want me to put it up tonight?
Yes, because I came in like halfway late into your class, and I'm like, damn it, I want to kind of have everything put together.
I can put it up tonight.
Thank you.
Yeah, no problem. Rich, question?
Okay.
You there, Rich?
I am, Greg. Hi.
Hey, how are you? Yeah, I can hear you.
Cool. Hey, I had a question about using a calculator. Do you get docked on the GRE for using the calculator? I heard that.
No. In fact, I use the calculator a lot.
Okay. Cool.
Yeah. No. The only thing I'll say is make sure you use it with the keyboard.
Okay.
Don't use it with the mouse clicking because that'll kill your time.
Okay. Gotcha.
Yeah.
All right. Thank you.
Okay. All right, everybody. I think we are good. Hopefully you found this interesting because I think if you start approaching math from a different perspective, you'll find this shit is pretty fascinating. I mean, it really is. I mean, just kind of like the time and the patience it took to figure out even something as, something we take for granted like zero. That took millennia to come about, right? Okay. Tao says, how do you use the keyboard? You just hit the numbers. You just use the number pad and you hit the star, the asterisk to do a multiply. Yeah, that's all. Okay. All right. So everyone, if you can start approaching math from kind of a different angle, more from this kind of historical perspective, and I think you'll find it a little bit more enjoyable. Okay. All right. I'll talk to everybody later, and I'll have this class up tonight. Okay. Talk to you guys later. Bye.